our ordinary accepted notions of space, time, and movement do not correspond with reality, and that the laws of nature require to be all reformulated on a new principle which rests primarily on the rejection of space and time as constant factors. To the metaphysician, there is nothing subversive or revolutionary in the new principle. It is practically identical with principles which have, time and again, been formulated in philosophy, ancient and modern. But to the man of science, it seems like a sudden upheaval of the foundations on which the whole stupendous structure of modern science has been reared. Einstein's Principle of Relativity has two distinct stages. The first formulation, in 1905, expressed the acceptance of the consistently negative results of experiments contrived to determine absolute velocity by reference to a fixed system at rest, such as the ether of space was generally supposed to be. If there is no zero system with reference to which absolute velocity can be measured, we have to correlate observations for systems moving relatively to one another. The special principle of relativity, or the restricted theory, is so called because it applied only to uniform rectilinear translations of reference systems, and not to rotations or non-uniform translations. The special principle is that the velocity of the propagation of light in vacuo is constant for every observer, that it is unaffected by the translation of a reference system relatively to other systems, and that the constancy of the velocity is maintained by a variation of space and time. In 1917, Einstein formulated the new principle of generalized relativity. This was the extension of the earlier principle to include the law of gravitation and, by implication, all laws of nature. It accepted for all the laws of nature the impossibility of any absolute standard of reference, and it proposed to determine all universal laws as observational facts to be deduced from the movements of various systems relatively to one another. It involved the rejection of Newton's concept of the attraction of masses acting at a distance from one another in a uniform space, and even flowing time, and the denial that any spatial or temporal dimensions are uniform and absolute for all systems of movement. It also rejected the postulates of Euclid as impracticable. To make the full significance of this new principle appear, and to show its philosophical importance in the worldview it discloses to us, is the aim of the present historical study. It will be sufficient, before trying to follow the problem from its origin, to indicate clearly the two facts which the special and the general principle take to be conclusively established. They are both negative facts, and therefore have none of the simplicity of new discovery of the hitherto unknown. They do not give us new notions, but they upset our old notions, and complicate and render difficult the necessary reconstruction of the world view. The first fact is that the velocity of light is a finite velocity, and yet absolutely uniform for every observer, whatever the velocity of his system, and whatever the direction of its movement of translation relatively to other systems. The nature of light is not in question, For whether we accept the corpuscular or the undulatory theory, we know that light is propagated in a movement radiating outwards in every direction from its source, which is thus always the center of a sphere. The velocity of the propagation of light in planetary space was discovered in the 17th century. The telescope had revealed the moons of Jupiter, and in 1675 the Danish astronomer Rømer observed that there were differences in the periods of their eclipses, and also that these differences corresponded with the changes in the position of the planet in its orbit, and therefore in its distance from the Earth. This proved that there is a time interval between the emission and reception of the light. Rømer calculated the velocity of this propagation with extraordinary accuracy, which subsequent experiments in the laboratory have confirmed. It is a velocity which for all terrestrial distances is negligible. It only becomes of account in the great spatial intervals which separate planetary and stellar masses. We have no other means than that of light signals to enable us to determine the simultaneity of events. And yet, light signals are themselves subject to the interval required for their transmission between the observers at distant points who are using them. Now, if space and time are absolute, as we ordinarily suppose, then when distances and intervals are varying by reason of the movements of the observers relatively to one another, it is quite clear and evident that the velocity of light for the observers must vary correspondingly. But experiments specifically designed for the purpose have proved conclusively that the velocity of the propagation of light does not vary. It is uniform for all observers, whatever the relative movement of the systems in which they are situated. Let us take an imaginary case and suppose that two observers of the same events are in different systems of reference, and that each observer, thinking himself at rest, sees the other system moving with a translation of 100,000 miles a second. That is rather more than half the velocity of light in empty space. Now, it would be rational to conclude, and we should naturally expect to find, that if these two observers communicated with one another by light signals, the velocity of the propagation of the light signal would be more than twice as great in the direction of the uniform movement for the one observer than it would be for the other. But if we reason from the negative results of the actual experiments, this would not happen. On the contrary, the velocity would be exactly the same for each observer. So the principle of relativity declares that the velocity of light is constant. However, the conditions of the observer vary by reason of the translation of the system, and that space and time are different for different systems. To ordinary reason, this is a paradox. Einstein has accepted the experimental proof without any attempt to explain it away as appearance or illusion. He formulated the principle of relativity to accord with the result of the experiments. The principle is, then, that the velocity of light is constant and that space and time are variable. I am not at present inviting attention to or challenging criticism of the evidence for this fact, so subversive of ordinary ideas and upsetting to our habits. I am trying only to state as definitely as possible what the fact is. Certainly in the case of the enormous velocity of light and the infinitesimal fraction of it represented by any known velocity of translation, the fact, if we accept it, is negligible as applied to our common terrestrial life. But it is very difficult indeed to reconcile with our experience of velocity generally. Sound, for example, is a propagated movement. But when the source of sound is moving with us, as when we're talking in an open motor car, we naturally adapt ourselves to the idea that the sound waves are not spreading with equal velocity forward and backward. We think, wrongly perhaps, that the waves of sound, when we in the car are moving in their direction, spread out from the car at a lower velocity than when we are not moving with them. The special or restricted principle of relativity, then, is that the velocity of light is constant for all observers and independent of their system of reference, and that space and time are variable, dependent on the relative translation of systems. The general theory of relativity goes much further. It extends the principle to all the laws of nature. It rests upon a fact, or rather upon a negative discovery, a discovery which is not due, as in the case of special relativity, to definite test experiments, but the result of the successful application of the principle to the formulation of a new law of gravitation. The proof of the new principle rests on the fact that it has been found to account for a well-known discordance between the astronomical calculation for the precession of the perihelion of Mercury and the actual observation, which had previously baffled all attempts to explain. Further, it enabled a prediction to be made as to the deflection of the light from a star passing near the sun during a total eclipse, which was verified in the observations of the eclipse of the sun on May 29, 1919. A further prediction by Einstein that the spectroscopic analysis of atoms vibrating in the gravitational field of the sun, compared with the analysis of similar atoms on the Earth, would show a shifting of the lines towards the red end of the spectrum, has at present not been verified, and is the subject of research. It is not, however, with the details of these tests of the principle which I am now concerned. I want rather to make plain the fact which is alleged as the basis of the new theory. As applied to the new theory of gravitation, it is called equivalence. If we raise an object and then release it, it drops. We explain this as an instance of the law of gravitation, by which bodies attract one another in a definite relation of their mass and distance. We regard the floor as fixed in relation to the earth, and the released object falls to it, drawn, we say, by the attraction of the earth. But the earth, to which the floor and the room are attached, is rotating on its axis. It is also traveling on its orbit at many miles a second, and the whole solar system is moving in the stellar system. It is clear, therefore, that there might be an observer who would say that the released object remained at rest and that the floor of the room moved to it. The theory of equivalence is that there is no way of deciding between the alternative descriptions, whether in fact the object fell to the floor or the floor rose to the object. If one observer had the right to decide positively for the one, another observer would have the equal right to decide positively for the other. If the principle be accepted, it completely negatives the idea that forces of attraction are exercised by bodies on one another in the sense supposed in Newton's law. If this negative fact be established, namely that there is no way of determining the actual line which two objects follow in their movement towards one another, and that contradictory descriptions of such movement are really equivalent, it follows that space cannot have the properties which Euclid required, and force cannot have the nature which Newton supposed. The discovery can only be compared in importance with the discovery of Copernicus, that the Earth is not at rest but undergoing a diurnal rotation on its axis and an annual revolution round the Sun. Space and time are concepts of the mind. They are indeed for all of us realities with which we feel we are in direct relation, a relation so fundamental that our whole existence depends on it. But space and time in themselves, though not abstractions, lack the concreteness of objects and events. They are a framework of the physical universe and give form and continuity to its content. As concepts, they are judged by their consistency or inconsistency. The dominant place they occupy in philosophy, and the persistence of the problems they give rise to throughout the whole history of philosophy, ancient and modern, are due to the inherent logical and metaphysical difficulties they present. But space and time are not only concepts, they are also images. In studying the theories of space and time, it is very important to take into account the imagery which supplies to the concepts their content. It is usual to neglect this completely. The reason is that philosophers never reveal the imagery which lies behind and supports the concepts they analyze. For imagery, we have to go to the poets. Pari passu, with the evolution of the concepts of space and time, has been an evolution of their images. Homer, Dante, and Milton are as distinct in the imagery of their expression of a worldview as Aristotle, Aquinas, and Leibniz are in their concepts of its reality. Every philosopher starts his reflection from the standpoint of his world view. The world view is an imaginative background of his thoughts. His reflections borrow their shape and draw their content from it, revolve round it, and always return to reform it. But when we study a philosopher's theories, we treat them in the mathematical method, substituting signs for images. We suppose there is a special advantage in this power of detaching the sign completely from the image in which it arose. As soon as we grasp a man's concept, we adapt it to our own imagery, whatever it may be, and proceed as though the world view were of no importance. A familiar illustration is the way in which the Bible is interpreted in Christian households. The concepts are detached from the imagery of the writers and fitted on to the homely imagery of the reader, whatever it may be. We study in the philosophers their logical principles and abstract concepts. In the poets, their imagery. We forget that the poets express the imagery which the philosophers require to embody their concepts. If we would reconstitute the thought of an historical period, we must read its poetry in conjunction with its philosophy. When we discuss today the theories of Newton, we take no account of the world view which presented itself to him, and of its complete difference from our ordinary worldview today. Our worldview is continually changing, and the imagery in which we clothe it becomes outworn and cast aside. How completely different, for example, is the world picture represented to us in Mr. Wells' Outlines of History, from anything which filled the imagination of a previous generation. I have chosen Newton as an illustration because we are accustomed to accept his concepts as essentially modern. Science has advanced, but his concepts remain of universal application. Newton's age is so near our own as compared with the Greek and medieval ages that we hardly appreciate how much its imagery has changed. Yet how fantastic the world scheme of Milton's Paradise Lost appears to us today, and how inadequate his imagery to embody modern concepts. It was, however, the familiar background of Newton's thoughts. Quote, "Now had the Almighty Father from above, from the pure empyrean where he sits, high-throned above all height, bent down his eye, his own works and their works at once to view. On earth he first beheld our two first parents, yet the only two of mankind, in the happy garden placed, reaping immortal fruits of joy and love. He then surveyed hell and the gulf between, and Satan there, coasting the wall of heaven on this side, night in the dun air sublime, and ready now to stoop with wearied wings and willing feet on the bare outside of this world, that seemed firm land embosomed without firmament, uncertain which, in ocean or in air." Unquote. Unlike Dante's world, heaven and hell have no direct connection with our universe, which is conceived as a system of sun and planets swinging in vast space, yet an ordered system with laws of nature imposed upon it. It is a new creation, espied from afar by Satan, and offering in its order and arrangement rest for wearied wings and a sphere for concerted action. But what strikes us particularly in such imagery as compared with that which we should now deem adequate is that the distant observer surveying our world sees it as it appears to us and makes no allowance for systems of reference. Our spatial and temporal coordinates are also those of God and of Satan. This was essentially Newton's view. The importance of imagery and the way in which it qualifies concepts may be illustrated also in a somewhat different way. Take the case of the familiar phenomenon of the ebb and flow of the tide, which we explain by the concept of gravitation. For us, the tides mean an alternate rise and streaming of the water in one direction, and a fall and streaming in the reverse direction, with all its minute and dependent circumstances. To an outside observer, the tide would mean only the unalterable shape a plastic body in rotation would assume, in spite of the changing position of the mass. Throughout the whole history of human thought, while imagery and concepts have been changing continuously, the fundamental notions of space and time and movement, both as being direct data of experience and necessary conditions of experience, have withstood all change. They appear to us as the framework of our universe, whatever the content and the nature and the history of that universe be. And yet, from the very beginning of our historical records of human reflective thought, everyone who has turned his thoughts upon them has found that they present insoluble problems and offer the strangest paradoxes. Neither our images nor our concepts of space and time are identical with anything spatial or temporal which we perceive. It is from this incongruence of percepts and concepts of space and time that the psychological problems in regard to them arise. Space is imaged either by its negative character as the void, or by its positive character as extension. But neither void nor extension is direct experience or a datum of sense intuition. Although space and time are intimately bound up with all sense experience, there is no actual sense experience of space and of time. We cannot, for example, satisfy in regard to the ideas of them a demand such as Hume proposed for a universal test, produce the impression which has given rise to the idea. Of space and of time there are no impressions. A still more surprising and even disconcerting fact is that while image and concept of space and time fulfill completely the Euclidean postulates and conform exactly to the axioms, not one of our senses gives us spatial and temporal experience conformable to those conditions. In his New Theory of Vision, Berkeley maintained that the sense of sight cannot yield a perception of distance or give us knowledge of the third dimension of space. And based on this, the theory that visual perceptions are a language of signs, the purpose of which is to enable us to anticipate tactile sensation. But tactile sensation will not give us knowledge of distance. Such knowledge depends on movement, the sense of which Berkeley includes in touch, and movement involves time as well as space. And so, then what is the absolute standard by which we are to measure time? Try in what way we will, we can never, by direct perception, arrive at the notions of absolute space and time, which yet we imagine and conceive to be the basis of the reality of nature. This is no new discovery. It is indeed a commonplace of philosophy and even of the modern science of psychology. One of the large problems of contemporary psychology concerns the nature and origin of the perception of space. There are numerous theories which fall, however, into two main groups. They are named the genetic and the nativistic theories. The genetic theories derive our notion of space from sense experience, which is not itself spatial, by means of inference and mental construction. The nativistic theories, on the other hand, derive it from the mind itself and the mode of its activity and experience. A genetic theory has been held by most of the older as well as by many of the present generation of modern psychologists. An illustration of it is the theory expounded by Herbert Spencer, Principles of Psychology 2:178, according to which the perception of space is simply an interpretation of the simultaneity of sensations, explained physiologically in the case of sight by the overlapping of successive stimuli on the retina, and in the case of touch by the reversibility of series of tactile impressions. Another illustration is the well-known local sign theory of Lotz. The local sign is not a localization or extension in the sensation itself, but a character belonging to tactile impressions which later causes the mind to locate them in particular points of the body. It is from these impressions that our mind is supposed by the theory to construct the perception of space. An example of nativistic theory is the view expounded by William James in Principles of Psychology, Volume 2, page 134 ff. That there are sensations to which the character of voluminousness distinctly belongs, and which are thereby able to give the mind direct perception of space. This character, called by other psychologists extensity, is not extension, that term being only applicable to physical objects. Extension is a sensible quality. Extensity is a character of sensation. It is not then in philosophy, nor in science of psychology, that the principle of relativity is revolutionary. It is only a revolution in physical science, and it is a complete revolution in science, because mathematics and physics have seemed justified in rejecting as outside their sphere and completely indifferent to them the problem of the relation of the mind to its objects. The objective character of physical science, upon which it has prided itself, has therefore come to mean the uncritical assumption of absolute space and time. The introduction into pure mathematics or into pure physics of a subjective element seems not only a sacrilege, but a downright betrayal of the very principle on which science is based. It has been supposed that in its purely objective basis lies the strength of physical science, and that to this objective basis is due the steady and rapid and continuous progress which is often vaunted as presenting a favorable contrast to speculative philosophy. When the principle of relativity was first formulated, it was generally put forward as a methodological principle, applicable only within the sciences concerned, and with no relation whatever to any question of general philosophical or metaphysical theory. It simply, it was said, proposed a reform of mathematical procedure, a reform which was radical indeed, for it involved not the correction or improvement of the accepted equations, but a new set of equations involving new constants and new variables. The general principle of relativity now proposed by Einstein is acknowledged, however, to concern the most fundamental philosophical concepts of the nature of the universe. The essence of it is to introduce the bane of the physicist, subjectivism, into the arcana of physical science. It shows that it is impossible to abstract from the mind of the observer and treat his observations as themselves absolute and independent in their objectivity. It requires us to give up the assumption of an absolute standard of reference for the measurement of the velocity of a system. It rejects the inference which all our experience and all our science has seemed with such increasing assurance to affirm, that beneath the objects we perceive, juxtaposed in the external world, there is an absolute space which would be void but not abolished if they were removed, and that behind the events which succeed one another in our consciousness, there is an absolute time which might lose all distinction if there were no events, but which would still flow. We are to reject this inference, not because it is found to be useless, not because pure space and pure time are undiscoverable, not because we can never by direct perceptive means become acquainted with them, but because physical experiments which ought to have revealed them if they exist have uniformly failed to do so. The new principle is not a belated discovery of our ignorance. It is a new advance in positive knowledge. In this lies its strength. The study of nature has revealed to us that the nature we study is not independent of the mind which studies it. There is no absolute physical reality which a mind may contemplate in its pure independence of the contemplator and the conditions of his contemplation. The new principle is that every observer is himself the absolute, and not, as has been hitherto supposed, the relative center of the universe. There is no universe common to all observers and private to none. The work of physical science is to coordinate the observations of observers, each of whom uses his own coordinates and for whom there is no common measure.